I'm going to draw two charged parallel plates. Doesn't matter which way I have these oriented, horizontally like this, vertically like this, whatever. Doesn't matter which plate is positive, which plate is negative either. If I draw the top plate positive, however, and the bottom plate negative, then the electric field will go downwards away from the positive toward the negative. I could have just as easily drawn it like this, with a negative and a positive, and the field would have went like this. Doesn't matter. It's a uniform electric field between these two charged parallel plates, and the field goes from positive to negative. Yep.
I have a question.
Okay, go ahead. Now let's put a negative charge, or sorry, a positive charge in between those two parallel plates. We know that that's going to experience a force, and because it's positive, the force is going to be in the same direction as the electric field. It's going to be downwards. Now let's draw two more parallel plates, both charged. One's positive, one's negative. Again, the field is a uniform electric field going downwards like this. Let's put the positive particle in there again, but this time let's give it an initial velocity to the right. We know that that particle is still going to experience a force downwards, and therefore it's going to be deflected downwards, although this time not straight downwards. Yesterday we learned the shape of the path, and we'll talk about that again in just a second. Where would we see something like this in the real world? Why are we doing something like this? Parallel metal plates. It seems like such an abstract thing. It seems like such a, I don't know, such a created thing just for the sake of doing it, as opposed to with any kind of real application here. Yeah. Ethan says spark plugs. Sure, the gap between spark plugs is like two parallel plates. Now it's a really, really small parallel plates and really, really close together, but in that area directly in between the gap of the spark plug that's used to ignite the fuel in the cylinders of your car, it would be a uniform electric field. So we'd have something that's like two charged parallel plates. Last year, you guys went on a field trip to West Edmonton Mall for your physics of amusement park rides. You guys remember that? I hope so. Oh, that's right. Yeah, that was, you guys were the first time in 38 trips that happened. But you rode the bumper cars, and the bumper cars have a metal floor and a metal ceiling. Actually, they switched them last time, I think, actually. For the last trip, they were a little bit different where they don't have the same system as they used to. Bumper cars at West Ed and everywhere else always used to use the same system where there would be this pole sticking out the back of the car and touch the roof of the bumper cars, right? You guys have seen that before, right? Even if it wasn't at West Edmonton Mall. One plate is positive, one plate is negative. There's a uniform electric field between those two parallel plates. And that electric field is what drives electrons through this pole from one plate to the other, which really, when that happens, right, when you drive electrons via an electric field through this pole, that's an electric current. And that electric current is what flows to the electric motor of the car and causes the car to be able to go forwards and turn sideways. We've got maybe something like this. Here's a cloud, the bottom of which has become negatively charged for some reason. And then we've got the Earth directly below it has a temporary separation of charge, such that that part of the Earth that's nearby that cloud has become positive, opposite to the charge of the cloud. Well, over a very localized area, that Earth is pretty much flat, right? Over the world, it's round, but over a localized area, we can consider it to be flat, which would mean there would be an electric field, a uniform electric field between the cloud and the ground, pointing from positive to negative, that looks like this. So we draw it like two charged plates, just two random abstract plates, okay? But this could be the thing that you see when you're analyzing bumper cars or when you're analyzing spark plugs. We're actually going to do a question, Ethan, in a couple minutes involving spark plugs. The kind of thing that you could see when we're analyzing lightning, going from the cloud to the ground or the ground to the cloud. Make sense? Good question. All right, now I got a couple questions of you guys that would apply whether we're dealing with something like the abstract diagrams that I've got on the board, or the bumper cars, or the cloud, or the spark plug, or whatever the case may be. This analysis would apply, right? We know the electric field between these two plates is uniform. What does that mean, uniform, by the way? If I talk about uniform motion, we're talking about motion at which the speed is constant. Okay, we're not changing speed. If I talk about uniform electric field, we're talking about an electric field that is constant. It's the same. It's not changing. So the electric field right here would be the same as the electric field right here, would be the same as the electric field right here. The electric field is constant. Same deal over here. Electric field, same. Everywhere in between these plates, the electric field is the same. We know this because the value of the electric field that exists between those two plates is dependent upon the potential difference between the plates and delta D, not the distance from one of the plates, but the distance between the plates. So it doesn't matter where you are, position 1, 2, or 3, the potential difference is the same and the distance between the plates is the same. That means the electric field is independent of where the charge is. Anywhere between the plates, the electric field is the same. Same deal over here in the second diagram as well. Now, if the electric field is the same, what do we know about the force? The electric field is constant. What about the electric force? Let's say you got a charged particle, the green one right here, then we move it down here, and then we move it up here, and then we move it right there. What do we know about that charge, the force on that charged particle when I move it around? It's the same, right? We also know, in addition to this equation, delta V over delta T, we also know that the equation for an experiencer applies. E is equal to F over Q. And if I take that equation and I rearrange it to get F is equal to Q times E, if the charge is the same, no matter where the charge is, and of course it is, and the field is the same, no matter where the charge is, if these two things aren't changing, then the force has got to stay the same as well. The electric force is the same no matter where you are in between these two charged plates. If you take a balloon and you rub it against your hair and you put it right close to the floor of the bumper cars, it experiences an electric force. If you put it really high up close to the ceiling of the bumper cars, it experiences exactly the same electric force. Finally, what about acceleration? What about acceleration? Well, if the force on the particles is the same no matter where it is, and acceleration is force over mass, then what do we know about the acceleration of the particle no matter where it is? It's the same. It's constant. Let's use this room as an analogy for a second. Okay, we got a bottom plate and a top plate. The bottom plate is the floor, the top plate is the ceiling. But we're not talking about an electric field in this room. We're talking about a gravitational field. We know there's a lot of similarities between electricity and gravity, though. If I put this eraser near the bottom of the floor, near the floor, right, and then I put it up close to the ceiling, what do we know about the gravitational field that it experiences in both of those positions? It's the same. It's 9.81, right? It's 9.81 down here close to the floor. It's 9.81 up here close to the ceiling. Agree? The gravitational field is the same no matter where this eraser is in this classroom. The field doesn't change. High up, low down, over there, over here, the field is going to be the same. What about the force of gravity on this eraser? How does that change when I put it really high up close to the ceiling versus down close to the floor? Put it towards the back of the room versus towards the front of the room. How does the force of gravity change on this? It doesn't. The force of gravity is the same up there, down here. Agree? What about the acceleration of this? Say I drop it right here close to the floor. What's the rate of acceleration? 9.81. What if I bring it close to the ceiling and drop it? It accelerates at 9.81. So just like with gravity, the field stays the same no matter where you are between the plates. The force stays the same no matter where you are between the plates. The acceleration stays the same no matter where you are between the plates. It's exactly the same as gravity. And we talk about Coulomb's law, Newton's law of gravitation, electric fields versus gravitational fields. We're talking about electric field, force, and acceleration between two plates. It's exactly the same as when we have a gravitational field as well. Now, somebody in the last class, I thought asked a good question. Said, to the effect of is the field here always going to be the same as the field here? It's like the person said, when you go from one place to the other on Earth, the field can change, right? Top of Mount Everest, it's certain value 9.75, let's say. In New Orleans, it's below sea level. It's something like 9.83 or something like that. The field can change. Absolutely. Absolutely, the gravitational field can change depending upon where you are on Earth. This is one location. This is another location. The numbers that we get for this one aren't necessarily the same as the numbers we get for this one if the distance between the plates are different or the potential difference is different. Okay, but within this system, just like if we stay in New Orleans, okay, within this system, the field's not changing, the force isn't changing, the acceleration isn't changing. If we go to the top of Mount Everest, all those numbers may be different than they were for New Orleans. But at the top of Mount Everest, no matter where you are at the top, the field stays the same, the force stays the same, and the acceleration stays the same. One more quick little thing. What's the shape of this path? Ends up falling? Yeah, we got a downward force on it, right? And that downward force combined with its horizontal inertia ends up following a parabola. And then once again, that's just like gravity, right? When I throw this eraser through the gravitational field, the downward gravitational field causes it to follow a parabolic path. All right? You had 2 questions for homework last night. Page 568. Let's take a look at both of those now, if we need to, that is. Both, I think, compared to the stuff that we were just looking at, the difficulty of what we were just looking at, I think these are actually pretty straightforward. Any issues with either of these questions though, before we move on? No? All right. I want to give you a few questions for homework then. You may have a few minutes to work on these in class. You may not. Sorry, it's not these ones. The ones that I wanted to give you were the rest of the questions on worksheet number 8. Questions 9 through 12 on worksheet number 8. A question number, no, sorry, 10 through 12. 10 through 12, sorry. We already did questions 1 through 8, right? Question 9 is just like question number 8. If you want to do it, feel free to do it as a practice question, but you don't need to do it for homework tonight. I want you to do questions 10 through 12 because they're based on this whole parallel plate stuff with the electric field. Yep. Yep. All right, there are 2 multiple choice questions I want to do in class here. And those 2 multiple choice questions appear in your worksheet booklet. Questions number 47 and 48, and they both relate to this information that you see here about automotive wiring. I'm going to give you a little bit of help on this only because when this appeared on an exam in 2001, I believe, so 15 years ago, not because it's a crazy hard question, but because in 2001, we needed to know about transformers. The whole idea of transformers was a curriculum objective. Now it's not. So you had more background knowledge when you did this question in 2001 than you do now. I'm not going to explain how a transformer works, but I will tell you that the purpose of a transformer, it changes my potential difference from a low value to a high value. It can also do the other way around, but in this case, from low to high. So we're changing it from 12 volts over here to 20,000 volts over here. So when you do this question, analyzing the spark plug, you're not going to use the 12 volts because the spark plug is on this side. You're going to use the 20,000 volts. Does that make sense? You would have known that yourself 15 years ago, but now because we don't have to learn about transformers, they ever give you a question like this on an exam, they'd have to provide you with a little bit more information like that. All right, let's get to work on those 2 questions. I'll take a look at them when you're done. Question 47, pretty straightforward actually, question 47. We want to find the electric field strength induced in the gap of the spark plugs. All we're going to do is say E is equal to delta V over delta D. Connor asked earlier about applications for this. When do we ever see this in the real world? This is one of the situations we see it in the spark plugs, as Ethan pointed out to us. Delta V was 20,000 volts. And the distance between the plates was, I think it was, 2 millimeters. So we're going to say that's 2.0 times 10 to the negative 3 meters. And we do the math there, it works out to be, I believe, 1.0 times 10 to the 7 meters. Volts per meter. Or you could say newtons per coulomb. Both of those work. D. How many people get D? Good. Good. Pretty straightforward question, right? 48, a little bit more challenging here. What other equation besides E is equal to delta V over delta D are we allowed to use when we have two parallel plates? Remember that Venn diagram we drew? The producer equation, the universal equation, the parallel plate equation. Which one is it? Yeah, we're allowed to use E is equal to F over Q. If we want to find the acceleration, we know to find the force. How are we going to find the force? F is equal to Q times E. We know the electric field, we know the charge. 1.6 times 10 to the minus 19 times the field of 1 times 10 to the 7. That's going to give me a force of 1.6 times 10 to the negative 12. Now, if I want to find the acceleration, I'm just going to say A is equal to F over M, as I always do in Physics 30 when I'm looking for acceleration. Force is equal to mass times acceleration. 1.6 times 10 to the minus 12 divided by the mass, which is 9.11 times 10 to the minus 31 meters per second squared. Do the math there, and I believe the answer worked out to be 1.8 times 10 to the 18 newtons per kilogram. That should have been kilograms. Newtons per kilogram, or it could have been meters per second squared, either one. We'd express that looking for A, B, C, D, 1818. The base, and then the exponent. How many people got that one?